It is visible.
Yeah.
Yeah, welcome back, dear participants. Now we will have the second session for today on overview of geographic information systems. It will be delivered by our guest faculty, Sri Harish, scientist SF from National Remote Sensing Center, Hyderabad. So I hand it over to him for delivering today's session. Thank you.
Yeah, thank you, Chaitanya sir. So good afternoon, everyone. Yeah. So welcome back to this afternoon session, where we'll be discussing about the geographic information system. Because we have a very short session on this particular subject, and moreover, I'll be covering different components of GIS. I'm restricting myself to the overview. So probably some of the keywords or any concepts related to this presentation. So if you're, not very clear, probably anyway, we'll have a separate question answer session. But my request would be to kindly explore the internet, or you can Google some of these keywords to have a better understanding. I'll try my best to give a conceptual understanding of what do you may understand by GIS and its components. But I urge you also to kindly have some exploratory exercise related to this particular subject. But okay, then we'll start on this subject of geographic information systems. So as you have seen in the morning session, like GIS or the geographic information system is one of the key components of this geospatial technologies. So where you have satellite technologies for capturing the data, for measuring a lot of data of the natural processes or the man-made processes, capturing the imagery, understanding the our climatic system, our weather system, and also deriving information out of that one. So we have various instruments on board the satellite platforms, right? So you'll see, like apart from such systems, we need to also capture the other parts of the Earth as a system. So and convert them into a digital format, so that we can also combine these data sets with whatever we get from the satellite platform in order to develop a comprehensive geospatial data system, so that we can analyze better, we can model it better, improve our accuracy, improve our reliability, and improve our decision making further, right? So I'll try to touch upon some of these basic concepts related to the GIS in the coming slides. Right, so GIS, as you are all aware, it is a geographical information system. So we all understand geography. It is one of the core subjects, or you can say like core science subjects that is there for a very long time. Probably you are aware of the in the historical probably readings, historical books, the kings and the invaders using maps basically to they plan their voyage, plan their what you call invasion. So all these things I think are very much there with in our memory of how maps are being used to better. Okay, so probably I'm just giving an example so that we can all relate to what is that we are discussing about. Okay, so maps anyway later has become in fact map is the first scientific tool that was developed by the ancient man. Of course then other inventions, but a symbol piece of a graphic feature that is drawn on a cloth or a piece of paper, we have seen the importance of that one, right? So that is probably where the story of maps, GIS evolved, as and as we, further into the real world. Okay, so it is basically a system that will allow us to capture the geographical data. So now what is the geographical data that we are talking about? Now, when we see from an individual perspective, okay, so like if we just stand or look in front of us, we see various features, living, non-living, right? Okay, so that are basically a part of the world. We see people around us. We see a lot of geographical features, natural features, man-made features. So this is a part of our okay. So when we travel, right, or when we commute on the roads in vehicles, so we'll see a lot of real world targets. So that is capture in a GIS system. Okay, so whether it be roads or buildings, or man-made objects or natural objects. So how do you capture a tree? Basically, okay, so either you can take a photograph or of the tree standing from a distance, or you can pinpoint the same tree from a satellite imagery using a small, what we call as tag. Tag a tree or a building or a hospital. So like how we are navigating using maps. Okay, so basically we'll enter our starting location, we give our destination, and the system basically gives the optimum path. Okay, so that is an example of how GIS can provide you a solution. Okay, for basically navigation using the maps. So it is a very successful application that is used by the people around the world for their day-to-day activity, and that is based on GIS. Okay, so just to give you a solid example of where GIS is already the applications of GIS are already providing solutions to our day-to-day activities, right? So again, GIS is meant to study the same, the geography with from a slightly more detailed fashion. Okay. So previously, geography used to study about the various landforms. Okay, so how to basically map them, how to understand the different terminology of the geographic, mostly in a manual fashion or in a paper fashion. So with the advent of GIS, you see like a lot of things are now been transformed into digital format. Okay, and now we are experiencing the digital revolution, right? So where the capturing of the data, the conversion of the data, the storage, right, the analysis is probably done on the press of a keyboard button. Okay, so that is how fast the GIS has transformed. So GIS in itself is not a dedicated technology like the satellite technology. This is a concept that has benefited largely from the from the advancements that have taken place in the computing technology, in the display technology, in the visualization techniques. So it has borrowed many of these concepts from the graphic industry also, right? So the visualization, what you see when you work in GIS are basically drawn from the graphic industries of how to render them, how to keep that the quality of the graphics on a consistent node, even if you zoom in and zoom out. So probably GIS, I would say, like was a big beneficiary out of this one. Right, so now GIS, we are trying to understand with respect to the other components of the GIS, geospatial technologies, that is the remote sensing and also the navigation. So if you want to build, let us say, a world in a digital domain, so how we do it? So basically, we need to capture each and every what you call feature or object that exists in the real world in a digital format, right? So that is what we are going to do with the help of a GIS. Right. So GIS is a technological tool, as I've told you, like because of the advancements that have taken place in the computer domain, in the computer system domain, especially the processing, the computing, the storage, and especially the database management systems. So the GIS also benefited hugely from that one. So we can say like it is a technological tool, and now with the the web-based technologies available, cloud-based technologies available, it is going to only further enhance and enrich the user experience working on a GIS system, right? So we'll see like we can easily handle, multiple layers of geographical data very easily. So you can directly handle it in the form of individual files, or you can create a database out of that one and you can effectively handle that one, right? So the objective for any technology is to basically to give a reliable outcomes so that we can do proper forecasting. Especially I'm talking about the geospatial point of view. So to improve our forecasting, to give accurate output, right? But this is all again dependent on the data we used. If we don't use data correctly, if you don't process the data correctly, or if you don't use a correct methodology, probably you will not get the right output, right? So that's why we need to ensure like whatever the data we are collecting is processed correctly and in the right sense, so that when you actually do the analysis, we also give a better output, or let us say a correct output from the inputs that we are using, right? The overall objective is to to improve the decision making. Again, this decision making is subject to, as I've told you, like the number of inputs that you are using, okay, or the optimum number of inputs that you are using for doing a any analysis or a study, right? Fine then. So there are some very basic questions that we need to understand with the geographical data. Like suppose if you want to map the roads, if you want to map the infrastructure, if you want to map, let us say the automatic weather stations. Okay, so basically you need to have the basically the coordinates of these points, or you need to have the locations of each and every node that you have created with respect to the the roads, okay, or you need to geotag these buildings, whatever you see, I mean, on a daily basis, okay. So we'll try to understand like how the GIS with the help of its the geometry and also the attribute information plays an important role, especially for capturing the the real world information, okay. So the satellite is actually giving you the factual information. So we need to convert that factual information into some labels or some meaningful values that is representing a physical parameter, or it's the category of that particular pixel, right? So that is what we do with the satellite imagery. But in a GIS environment, we build the what you call the geometry and also the attributes of these real worlds from the scratch, right? So we are getting already the surface information from the satellite imagery in the form of pixels, or let us say in the form of maps, or in the form of thematic information, or some geophysical parameter. Like let us say if you're getting at temperature data or rainfall data, you can directly get from this what you call, you can use the satellite data to arrive at that one. But with the GIS environment, we need to create everything from the start. And we see like in the real world, like most of the phenomena are time dependent, okay? Not, I would say, time dependent, but they are based on time. Like you see, like we have our regular office timings, and we during this rush hours only, there will be a lot of the staff there, right? Okay, so all these things, how do you basically capture such information and put it in a GIS is what GIS will help you to do. Okay, so that means you can capture the geometry. That means whether it's a what you call, it's a building, whether it's a road, whether it's a, let us say, an automatic weather station or an hospital location. You can also measure its distance from a particular location. You can see what is it there in the neighborhood. Okay, you can also map the relationship, so which is another thing that is naturally existing in our real world. Okay, although we don't see explicitly like on the surface on where when we look at it, but we can still say like all the spatial entities or all the geographic entities do have an intricate spatial relationship among themselves. Okay, so that means I'll give an example. Like if you have to reach a particular destination. Suppose if you start from your home and want to reach an office, you follow a particular path that will help you to reach your office in a very let us say in an optimum time. Okay. So what you do is basically if the roads are not connected, so it will be very difficult for you to navigate that particular path on a given day. Let us say some roads are closed, and you do not know like which way to take. Okay, so there basically you have a confusion like which way to go or which way not to go. But if you feel like there are connected roads that are available in this region, right? So either through maps or from some field information, then you can help yourself navigate to the correct location, right? So there is a spatial relationship among the different geographical entities that we can also build in GIS. Okay, and as I told you, like some geographical entities are time dependent. Their spatial dependency is there, spatial relationship is there, and also like the temporally also they have some relationship. Okay, so that means some are short, some exist for a time being, some are permanent. Okay, so like temporal relationship can also be built or can be included in this GIS environment if we know their attributes or spatial relationship like this. Okay, right. So as I've told you, like what we see in the real world is basically what we want to capture in a GIS system. Geographical entities or features have spatial relationship. They are interactive. They are interconnected, right? Right. So how do we basically make sense of all these things and how do we capture? So this is basically the crux of what GIS is trying to solve. Okay. So because we already have a lot of data in the form of the topographical maps. Okay. So as I've told you, like the map was the oldest GIS information that was available before the digital era started. So we can use those maps to start with and the satellite imagery to basically capture the real world information in a digital domain. Okay. So then we see like this GIS now as advanced spatial analysis tools. You can use them to model, to find out the what you call the network analysis. You can do a lot of what you call this transport analysis. You can navigate to a particular place in the best possible route, right? And then you can build the spatial relationship. So you can visualize a lot of events and phenomena in this GIS environment. Okay. Yeah, so we have what is known as the spatial data. Probably I need not emphasize what you mean by spatial data. So spatial data, so normal, conventional data comes in a tabular format. Okay, so tabular format, if you go to a particular weather station data, it will give you basically the serial number, the latitude, longitude, the name of that particular weather station, and what was the rainfall or the temperature recorded for that particular location. So in a way, like that is a tabular data. But because you have this coordinate information or the lat long, we can convert that into a spatial data. So now instead of just plainly visualizing the tabular data, we can visualize in terms of in terms of a map. Okay, so you understand map, like where it is located. Okay, so where it is located, whether it's located in Telangana or Andhra Pradesh or in Karnataka, and in which part of the country. So if you have the lat long, it can be easily represented in the form of a map, right? And we can visualize the data. And once you have data in a spatial format, your brain automatically starts to map the relationship between these points or various features. Okay, so that is how spatially we can investigate the problem better compared to a tabular data. Okay, Right. So you can see here, like these are all basically the locations of the automatic weather station in the state of Telangana. So this information I've collected from their their website. Okay, that is the planning and development website. So we can, as you can see here, now this makes a better representation of what is that I'm trying to visualize. So these are the automatic weather stations, and I can see like where they are located, in which location, which part. Probably if I have the district boundary map also, I can visualize it much better. I can see where they are densely located, where they are spacely located. So one can naturally imagine like where there is less dense location of these points. It could be mostly deserted, I mean forested area, or it could be a river, or it could be a water body, or it could be a reservoir, something like that. Okay. So this gives a better understanding of the problems that we are trying to deal with. Okay. Yeah. So as I've told you, like with this spatial data, I'll also get the attribute information. So attribute information is basically the descriptive information that comes with each and every. Okay, so we'll see in detail like what you mean by geographical features. So we can also understand some of these attributes, like what is it, as I've told you, like descriptive nature, what it is, where it is, what the name, what is the lat long, right? So all these things can be visualized with the spatial data. So here we have the graphical information, that is the point, and also the attribute information. Okay, so where did I get this attribute information? It was already made available. So I only basically what you call downloaded the data, and I've just tried to give a representation of this spatial data. Okay. Now from the satellite imagery that we discussed in the morning, so this is again an example of multispectral satellite data. So why it is multispectral? Because it is in a, you're seeing a lot the details in lot of color. Okay, so although the color is not truly representative of what we see in the real world. Okay, so this is called as false color. So it is clearly showing you the region of the the Hyderabad and to an extent its surroundings. So you can see three big lakes, one in the center and two in the southwest region, right? So basically, a satellite image gives you the continuous data. Continuous data means like you see like the entire terrain is captured and all the features are captured. So in fact, it's a very solid representation of the surface on a given particular date and time. So this was actually the 2023 image that I've downloaded from the USGS or the Copernicus website. So it is showing you, in good detail about all the geographical features as captured on that day. Okay. So now you can see here, like this is also an example of a spatial imagery, although we call this as a satellite imagery. It also can be called as a spatial data, where each and every pixel is has some coordinate information. Just like in the previous slide, you saw each point having lat long. Here, each and every pixel is has its coordinates. It has its latitude and longitude. But again, we'll come to the sub and all those things, how they differ and how to interpret them. Okay, right. So this is basically a continuous data. That means you are seeing every feature in detail. That means detail provided at this particular resolution. So this is a 10-meter multispectral data. So the pixel size is around 10 meters. Okay, right. So now how do we capture basically different features that we see in the real world, right? So we need to basically have a model that is good enough to capture the detail, right? So what is the detail? Like I want to capture a building, I want to capture a road. So why you want to capture road? Because I want to represent it on a spatial map, or let us say in a GIS layer, so that it will help me to understand that particular feature very comprehensively. Similarly, I want to map the network of rivers, network of roads, the network of underground drainage system, or let us say the optical fiber cables. Okay. So how do we basically map all these things? Although they are not visible directly from the surface, like if you go to that particular department that maintains a database of all these, what you call activities. I mean, where the lines of water supply is there, or the drainage is there, or the cables are there. So probably you'll get that information. But just I'm giving you an example. Okay. So it should be the model, the data to encapsulate those information. Okay, so what is that feature? What are its attributes? What is its geometry? So if we can capture those essential properties of a geographic surface, that model basically will help us in understanding the the entire surface. Okay, so that is where we use a geographic data model, that is to capture the geographical features, right? And there are multiple ways in which the geographic data model helps us, right? So one is like, because we are capturing it in a digital format, it is very easier to capture, to store, and also process. And once you process the data, you can share it with, you can publish it. Okay, so there are various sources that you can publish it, right? And now the computers are coming with I would say very reasonable and sound processing specifications, processing in terms of their GPU or CPU. They are, even a budget laptop or a desktop system is giving you that good computing power, RAM, and the graphic capabilities. So we can do a quick processing of the data that is available to us, either the satellite imagery or the data that we have created on our own, or we have downloaded from, let us say, from a web service, or a freely available GIS data source. So we can download these data sets and we can start working on. Okay. Right. So we have seen like satellite data is an example of a continuous data because we are seeing the entire terrain. Okay. So only thing is like if you want make a cover the entire region, you need to make what is known as the image mosaicing. Okay. So it's a image processing technique that will help you to stitch images that look continuous. Continuous means like if you want to see the entire India satellite imagery. So you need to stitch basically dozens of images together in order to get a layout. Okay, so that is called as a continuous feature that is captured by the satellite, right? And there are also the discrete features. Discrete means, as I told you, like I'm only interested in a particular aspects of the real world. So what are that aspects? I want to visualize only the road network or the water body network, or the only the buildings, let us say, or the automatic weather stations that I've shown you in the previous example. So if you are very discrete, that means if you are very choosy about what you want to represent. Choosy is not basically an option that comes to us, but we are very specific as to what part of the real world we want to understand. So for a, let us say, a people who is working on the roads, let us say R&B departments, so they will be interested in roads and the buildings related features because that is their department. Similarly, a logistical person will be interested in how we can plan so that he can optimize his services to various locations in the city. So these forms very basically discrete, or I mean a very selective piece of real world information that people want to capture and save it in their GIS environment. So these are again the different forms of the continuous and the discrete data. Okay. So satellite imagery is an example of continuous data, and discrete are basically, as I told you, like you can be specific about what is the type of feature that you want to capture in a GIS. Okay, so it has like some properties, like they are very what you call they have a specific boundary. They can be easily delineated. Discrete features, whereas continuous features, they appear together in a satellite imagery. Right. So we need, as I've told you, like we need to capture these geographical features, which are continuous in nature, which are in discrete nature, to basically, to derive a lot of information out of that one, to improve our understanding, also to improve our decision making, right? So we have basically the continuous data, like your satellite imagery or the even the elevation data, contour data, rainfall data, right? Okay, so these are forms of the continuous data. And in discrete, as I told you, like they have specific, what you call, they are delimited. So they have specific boundary, they exist in a particular location. Although they have the same type of, let us say, of the category in different location, but they exist in a particular location. Like monuments, if you see, so they have, specific location in which, they are built, and we need to go to that particular location. So networks, basically your road networks, rail network. So if you have to, let us say, navigate to a particular place, plan your journey, or you want to reach your destination. So all this, some of these examples, I think we are very familiar with. Okay. Um, probably, probably the railways has also started a feature where you can, find out whether the train has is on time or it is delayed. So they have a different, service available, but not in the form of a GIS. But surely, I think it will be implemented in the coming days. Okay, like so, if you want to, study an event, you want to, investigate a particular event. Let us say you want to assess like how much damage was done by, let us say, the recent rainfall event in Telangana. Okay, or there is some riot event is there, or there is a damage due to the earthquake. So all these things can be captured in a GIS environment with the help of the data, and we can interpret, visualize, analyze, and model such events or behavior in a GIS environment. Okay. Right. So GIS data comes in various forms and formats. Formats again are basically in different ways you can capture the same type. Right. So you have the spatial data, which is again categorized as vector, raster, and of course the three-dimensional data. But specific to the GIS data is the attribute data. So as I've told you, like the satellite data is already giving you the what you call the essential information in terms of the value it has captured. Okay, so from the let us say satellite data, you can capture what is known as the reflectance information. Okay, reflectance is basically a property that is dependent on the type of material it is or the condition it is in. Okay, so from the so that value is already captured. That means the attribute information is inherent in satellite imagery, whether it be reflectance, whether it be temperature, or it is rainfall. Okay, so either we can derive that data, or there are sensors that directly capture the attribute data. So the reflectance data is already available with the satellite imagery. But if you want to capture the attribute data of the GIS layers or the GIS data, we need to create the data from the scratch, or if the data source is already available, you can download. Another thing is, important thing is the metadata, which is basically gives you basically the summary of what the GIS data is all about. Okay, so these are some of the examples of vector data, right? How the raster data looks. We'll come in, in brief about all these types of spatial data. So vector, raster, and also the 3D data. And attribute information, as I told you, is the descriptive data of that particular feature. Okay, so whether it's a road feature, as I told you, like it could be any feature. What you see in the real world, if you can capture it in a digital format, then you can also attribute or give some attributes to that particular feature. Yeah. So then comes the metadata, which is, as I've told you, like it basically, quickly summarizes what that data is all about. So this is important, especially for the, for the companies who are working in creating a lot of GIS data. Okay, so that means what is the purpose of creating data, who has created it, who is the owner of that created, what data, what you call geographic reference system he has used, what is the purpose of creating the data, who can use the data, what is that accuracy of the data. So all these, summary of the data is provided in the metadata. Okay. So before you start working, just have a glance at the metadata. You will get to know some like the summary of the data so that you can use the data. And sometimes the usage also is listed. So who can use, who cannot use, whether we have to take separate permissions for the data or we can freely use the data. So such information is also provided in the metadata, right? So as I told you, like metadata helps you in probably classifying this GIS data. So you know like what is the type of GIS data you are using, whether you are using the data of buildings, you are using the data of, let us say, the population, you are using the data of the roads, the lakes, or the infrastructure. So it makes, because it is already given in that meta data listing, so it will be easier for you to understand what is the role of the data, what is the purpose of the data. Okay. And as I told you, like who has created the ownership, what is the spatial reference system it is used, is using. Okay. Spatial reference system is the coordinate system. Okay. So for which purpose it was created, whether it was created for public use, or it was created as a part of a project, or it was used for some commercial purpose. So what are the usage terms, right? So whether there is any license fees there, or we can freely use this. So probably in detail, it will give you such ownership records also. So you can evaluate. That means, as I told you, like the precision or the accuracy is also given in that one. So whether you will get to know or what scale it is used. Okay, what scale and what is the legend is used. So all these things will be given in the metadata, so that before you start using any publicly available GIS data, there are plenty of such layers that you can download from many resources that are available in the internet. But again, as I told you, metadata will help you to understand the real purpose and the usage of these GIS layers. And we also have this national standard for this geospatial data. So that again basically gives the standards for the different formats for the metadata that we need to follow. So if you are doing, let us say, a national project, GIS project for the country, so sorry, I'm not able to recollect that agency. Okay, so it has framed a broad guidelines or the standards for what are the metadata for standards we need to follow if we have to basically use it for national projects, so that all the contractors or the companies who are working for that project can exchange the data without any issues. Okay, so there should not be issues of interoperability, or like you give in some format, the other person is not able to read that one, or he gives you in some format, you are not able to use that one. Okay, so that means the normalization of use has to be is done only through standardization. Okay, so there's no one-to-one understanding between companies, but again it is a very broad-based guidelines or the standards that needs to be implemented for a national projects. Okay. Yeah, so this is about the metadata. So like you can see, so this is a very simple example of how a simple metadata looks like for a geospatial data. So they can see like who is the creator, what is the title, okay, when it was created, what is the file name. So all these things you can easily visualize in the QGIS also. So probably in your demo sessions, you will see like one click of a button will give you the entire summary of the data you're working with. Okay, so probably you'll see much more detail like compared to what is shown here. So again, there are, as I told you, like there are metadata standards, and companies or collaborators who are working on a GIS project need to strictly adhere to this metadata formats, right? In order to comply with the guidelines and the project standards. Okay. Right. So yeah, sorry. The NSDI is the institute that basically helps in Okay, so the National Spatial Data Institute basically frames that those guidelines and standards for the Indian companies. So whoever is working within this our country, we need to comply with those standards in order to make this data accessible to everyone across the country. Okay. Right. So it could range from a simple text file to a standard XML file also. Because there are different formats of the GIS data, the metadata also comes in different formats that you will find it in. If you explore in different softwares, you will see like it is, in a different format. But the idea is again the same. Like how do you find these details of who has created it, when these things can be easily understood from the metadata. Okay. And whether you can also, it also gives you whether it can, there is a further scope of using this data. Okay. So because let us say you already have a scenario where the data is already digitized. So why again doing the same work? So rather than that, what you do is you'll basically use that as your main GIS layer, and you add to that data in order to extend your the feature list or the whatever the data that needs to be digitized. Okay, right. So this is basically about the data models, data types. What is the spatial data? What is the attribute data? What is discrete, continuous? So all these things. But any data, when you want to represent in a GIS environment, it has to have a coordinate system. Okay. So just like how each and every let us say automatic weather station. So it has a specific latitude and specific coordinates. What is the latitude and what is the longitude? Similarly, for the satellite imagery also, like if you download the georeferenced data products, it will also come with all the latitude and longitude information. But for most of the data that you are going to do capture freshly, you need to understand in which coordinate system I have to capture. So before you start digitizing any GIS project, you need to basically create an empty GIS layer. So it will ask you like what type of shape or geometry you want to create, right? What are the typical attributes that you want to add to that particular layer? So all these things probably you will get to learn. I mean, those who are new to this GIS, I'm just, this is for you. But, when you create such layers, it will ask you upfront, what is the layer you want to create, whether it's a point, line, or polygon. What are the attributes you want? What is the coordinate system that you want to work with? Okay. Geographic coordinate system, whether it is a projected coordinate system. So it will ask you such information from you. So I'll try to summarize this particular next component of this session. Very briefly, because again, this in itself is a very huge subject. But you may be aware, like the Earth is represented in the form of a graticule network. Okay, so you can see here, like in this particular slide, there are some lines that are drawn on this sphere. Okay, sphere is basically a three-dimensional representation of a circle. So I think you are aware of this terminology, right? So if we have to divide this sphere into equal parts, so that is only possible through the help of the what you call parallels and meridians. Okay, so parallels are called as latitudes. That means if you imagine the sphere as represented by equidistant circles. Okay, so at the equator you will have a very big circle, and at the poles so it is basically a point, right? So these are basically parallel lines that are called as lines of latitudes. So the equator is basically the greatest parallel. We call that as the equator. And similarly, there are vertical lines which are called as the meridians. Okay, so all the meridians are basically are all of equal size. Okay, and also of the equal angle, right? So this system of dividing the Earth in a mathematical form or in a geographical form by this equispaced what you call imaginary lines of parallels and meridians, it is called as a graticular network, right? So with this network, so what it is trying to give you is like if we project each and every point on the surface of the globe from the center of the sphere, so it basically forms 2 points, 2 coordinates. One is its angle, from the center of the sphere. Okay, and also it's basically the what you call the one is the vertical angle, another is the horizontal angle. So by this mechanism, we can find out the location of any feature. Okay, so any geographical feature on the surface of the Earth. So this is broadly how the geographic coordinate system work. But we'll see like this is good for representation, but it is not very accurate when it comes to implementing on the real world. Okay, so why is because if we convert this, so here again, so we have what do you call? We have the marking starts from the 0 degrees. So it is divided into 90 degrees from the equator to the North Pole and 90 degrees from the equator to the South Pole. Okay. And similarly for the longitude, it starts with 0 degrees longitude and it goes up to 180 degrees. Okay. So we have basically the east in the east direction and also in the west direction. So that means the entire the globe is surrounded by the meridian, the what you call the meridians or the longitudes. Okay, so that means it is full 360 degrees, whereas the latitudes are from 0 to 90. That means 0 to 90 north and 0 to 90 south. So 180 degrees on the latitude and 360 degrees on the longitude. Only thing is like it is marked as north-south for the latitudes and east-west for the longitudes. Okay, right. So the only issue with this geographical coordinate system is the distances are not uniform across the globe. Okay, so in the only then the equator does 1 degree what you call longitude equals to 111 kilometers. That means anywhere near the equator only this what you call translation. That means translation of angular coordinates to the what you call the real world coordinates. Okay, that means if you convert these angles into straight line distances, they will match only in the equatorial region. But when it comes to the higher latitude regions or the lower latitude regions or in the poles, this mechanism does not work, right? So this is where the geodesy comes into with the help. So geodesy is basically the science and study of the geometry, shape, and size of the Earth. Okay, so mostly the shape of the Earth is considered as an ellipsoid. Okay, so just like how we have a sphere or a spheroid. A spheroid is basically it's a uniform solid spherical three-dimensional figure, whereas an ellipsoid is basically it's again a regular what you call three-dimensional figure where the axes are different. Okay, so that means we all know like the Earth bulges at the equator and it flattens at the pole. So that's why it is called as it is taken as an ellipsoid for most of the measurement purpose. Okay. So geodesy again is in itself a subject which the ancient geographers and voyagers have studied the Earth in using the various instruments. Okay, and they try to make sense of how the shape of the Earth is there. Okay, so we have what is known as the equipotential surface or the mean sea level. So this is the surface which is mostly used by the geodesers, geodesers to represent the surface of the Earth. Okay, so geoid again is basically is a surface that matches its ellipsoid at a particular location. So again, I'm not going into very detailed explanation of what you mean by geoid and ellipsoid. So ellipsoid again, as I told you, it's a three-dimensional surface. So it is mostly based on the mean sea level or the equipotential surface, we call it, no? Right? So this surface actually, as you can see, the green color, it is passing under the ocean also, right? So whereas a geoid, which is again, it's a representation of the same surface with respect to a particular location, because the Earth is a very big body. We cannot, have a true representation of the mathematics each and every location. Okay, And moreover, with the satellite, what you call observations of the, the gravitational or the, I mean, gravitational force experienced by the Earth. So that is also helping us to understand the true nature of the surface of the Earth. Okay. So that is your ellipsoid. That is the mean sea level. Okay. Then you have the geoid, which is basically the surface that is very close to that mathematical surface. And we have the actual surface, which is our topography. So that runs below the oceans. It goes on top of the mountains. So these are various descriptions that are given in this field of geodesy to basically understand the shape of the Earth. So why we are discussing all these things is because we'll see, like during the projections, we use different, different geoids with different datums. Okay, again, we'll come to what is datum and also the various forms of the projection systems. So I'll put it very, straightforward here, so that we'll not go into the, too many details. So the ellipsoidal model, as I told you, like it has a different, it is in the form of an ellipse on a two-dimensional, plane. But if you rotate this same two-dimensional plane 360 degrees, assuming that the center of this ellipsoid is in the plane of the, is in the plane, and if you rotate that plane, it will form an ellipsoid. Okay, so ellipsoid is like your watermelon. Just imagine like you have a watermelon, and that is how it looks like. Okay, and here if you see what is happening here, it is very, it has, because it's an ellipsoid, it has different major axis. That means x-axis will be different compared to the length of the y-axis. So from this, we can measure out what is the eccentricity and what is the flattening. So Earth, as I tell you, because of the huge mass and also the gravitational attraction in the solar system, it basically bulges at the equator. Okay, it bulges at the equator. That's why we have a different semi-major axis compared to the axis of rotation, right? So this is a model that is mostly used for describing the shape of the Earth and trying to match with the respective locations across the surface, so that we'll get a reasonable estimate or account of the measurements that are possible in a particular location, right? Yeah. So again, so what you see in a very spherical form is your what is called as the geoid of the surface, and the one that you okay, it is one that you see in that hash line is basically the datum. So datum basically approximates the surface at a particular location, right? Yeah, so we have local ellipsoids like the Clark 1866, similarly the Clark 1880. Then we have the global ellipsoid, that is a global reference system. Then mostly use the World Geodetic System 84, okay? And similarly, like the International Terrestrial Referential System, ITR, is also there. Again, so there are different types of ellipsoids that are proposed and used by different GIS software. So in QGIS, I think the EPSG is used. Okay, so the European Petroleum and Survey Group. So it has also a series of projection systems that can be used to represent this GIS latest. So that is what it follows. So ArcGIS use a variety of datums and also the projections for displaying this geographic layers. Right. So this is about the. Yeah. So the thing with this ellipsoids is like based on the mathematical treatment and the formulation, you see like there is a variation. So not all are same and match to the digit to digit, but they are very close. Okay, that means if your purpose is only for representation of the features and not for a very highly accurate measurement of the values, probably you can use any one of these ellipsoids. But when it comes to the accurate measurement only, you need to choose the correct datum or the ellipsoid or the projection system so that it will give you very accurate results. Okay, so you can see there is a variation between the equatorial radius, the polar radius, and also the flattening constant, right? So, but they are very close. Like if you're mapping it at let us say a very small scale. Small scale means global coverage. So if you want to capture the entire world, so if you see world maps, no, so you'll see all the continents, the countries in a simple A4 or A3 size paper. So how it is possible? because the scale is very small. Okay, so that means 1 centimeter will almost cover some thousands of kilometers on the map. So that is what mean by scale. The comparison or the the size of the real world objects as compared to what is represented in the map. So that is what the scale gives. So this is also dependent on scale. So if you want to have a very regional scale representation of the data, you need to wisely choose your projection system. But if your idea is to basically do a small scale representation, or let us say a national scale representation, you can you can still use. Sir, some I think interruption is there from the audience. Kindly mute so that we'll continue this discussion. Yeah, for
कौन अभी इसमें मैप कहाँ पे आपने उस समय दिया नहीं क्या वापस? लास्ट टाइम ने हमने जो मैप ले गया था, हाँ फिर क्या नहीं यहाँ पे नहीं बोले तो यहाँ पे क्यों नहीं रहते? हाँ ये है ना.
Hello, so can you mute your mic please?
यही दोनों यूज होते हैं आपके, ऐसे यूज किया आपने. नहीं यही तो, ये अभी तो ये दोनों नहीं सर, ये दोनों है, ये मैप और ये
Sir,
मैप दोनों.
please mute everyone, sir. It's disturbing.
हाँ नहीं लास्ट टाइम आपने इससे जो करवाया वही तो कमेंट करवाए कि ये ना काम करने.
So I request the organizers to kindly, mute the, the person who is probably is not aware that is online. Okay, so as I've told you, like for small scale representation, probably any of these global ellipsoids will do. But if you are looking at a very specific region or a specific location or region of the Earth or the country, you need to basically select the appropriate projection system and the data, right? Yeah. So for the global, like if you are representing the Earth as a globe or a spherical, mathematical spheroid, then this issue of scale and basically the translation of that angular coordinates into the linear coordinates will be a very inaccurate. Okay. So as I told you, like only at the equator, 1 degree equals to some 110 kilometers. So that is only true along the equator. But if you go to the different regions of this, angular regions of the sphere or the spheroid, they will basically change. Okay. So, and the issue is like sometimes if you don't, when you want to reproduce these global data to, let us say, local scale data, so that also will in fact create a lot of issue in terms of different properties of the map getting distorted, either in terms of linear dimensions or the shape or the direction. So all this can be a cost affair, especially when you are trying to doing the reprojection.
Kindly mute your mics. Yeah, please go ahead.
Yeah. So this is where the concept of map projections will come into picture. So this we are trying to understand how a curved, surface of a particular sphere can be flattened. Okay. So this is, conceptually we are trying to do that one. But only thing is, we need to do it in a proper, mathematical fashion, so that all the features that are on the, the curved surface are accurately represented on the plane surface. Okay. So that is where the map projection comes into picture. So it is basically a mathematical transformation that converts the 3D surface to a flat 2D map surface, right? So this is again, there are different types of map projections. So again, I'll be basically touching upon these things conceptually. So we have the cylindrical projection, we have the conical projection, we have the azimuthal projection, and then we have miscellaneous projections where a particular to match a particular region. So they have defined separate datums and also the combination of different projections, so that the regions, the properties of those features match in that particular region, right? So we'll see like quickly what are these types of projections. So what you mean by projection is like if you illuminate that sphere or the Earth as a sphere with a point source, okay, and you just fill this sphere in the form and capture it in a cylinder. So whatever the rays that pass through the different portions of the sphere and hit that cylinder, so that basically forms its projection. So mathematically, that is what we are trying to do. We are trying to convert this curved surface into a flat surface. Okay, so this is just an example to show like how different types of projections are used to convert the same curved surface into a flat surface. Okay, so we can fix a cylinder, as you can see here. Again, there are different variants of this cylinder. You can here you can see the major axis of the cylinder is parallel with the axis of rotation, right? So you can also fix the cylinder, that is perpendicular to this axis. So instead of the major axis of the cylinder, passing through the axis of rotation, it can be perpendicular to the axis of rotation, right? So I've not included that basically to make this one very simple. But again, within the cylindrical, there are different forms of projection. So you can see here, like in this cylindrical projection, also this particular figure itself will tell you, like in this map, the regions that are near the equator are probably matching. So that means their sizes are matching. But as you go higher up the latitudes, these regions are slightly elongated, right? So no projection system is perfect in terms of capturing the attributes of a map.
Everything.
So what we see in a map, right? What we see in a map basically is at what scale it is prepared, and what is the accuracy of that map in terms of the real world distances. So if I measure a point-to-point distance on the map, and if I want to, translate it onto the real world, so how far it is matching, okay? And similarly for, especially for navigation, if you see like, transatlantic navigation pilots who use these navigation systems, so they also need to have an, understanding of where they are heading to. Although they have the necessary instrument devices, the IMS devices that will basically tell you their location and where they are heading to. But still on a map, if they can see like where they are heading, so it will help them to navigate safely. So what are the these properties of a map? Basically, the properties of the map is whether the direction is preserved, whether the shape of that particular feature is preserved, the direction of the feature is whether it is truly not right, or whether the directions, whatever the directions are there, whether they are truly matching. So these are the some properties of the map that we need to essentially capture when we do the projection. So that is what we are trying to understand through the help of this projection. So cylindrical projection is a what you call mathematically very simple to explain these transformations. So that's why cylindrical projections are that is how they have evolved, right? And similarly conical. So if you fix a cone with the base almost parallel to the equator, and if you match the apex, that means this the planes when they converge and form a point, so that is called as an apex. So from this point, like if you again put a point source, illuminate the sphere, and then you basically match those projections of the light rays onto this piece of paper, then you will also get what is known as a conical projection. So there are cylindrical, they are conical. So conical is very useful, especially if you are trying to map the what you call higher latitude regions. Okay, so because the two what you call planes of the cone are transverse, that means they are intersecting with the surface of the Earth at 2 points. So where the higher latitude regions are also represented accurately in terms of their what you call angles. So once you have these angles, you will have the shape also properly represented in the map. Okay. So equator probably you can see there may be a small distortions because these rays have to travel a little farther, whereas higher latitude regions, they are slightly shorter. So like this, you can also devise what are known as the polyconic projections or the polycylindrical projections. So that you have a dedicated treatment of these particular map projections and coordinates in some of the what you call the reference manuals that are available online. Okay, so you can kindly refer them and try to have a fair understanding of what these are all about. Okay, so for every projection, you can see here like you can accurately represent these properties of the map. So and you can what you call generate what is known as a developable surface. Okay, so developable surface means the surface which is mathematically possible to create the same curved surface on a two-dimensional plane, right? Yeah. So if you fit multiple polygons, what you call cones, like now you can see there are secant what you call these planes are now secant. They are intersecting in multiple locations of this sphere, right? So all these because they are passing through those different latitudes. So all these features along that particular latitudes will be projected correctly. Okay. So again, there are azimuthal projections. So azimuthal projections basically preserve the the true angular directions. Okay, so we have the polar azimuthal projection, we have the equatorial. So that means you just put a plane tangential to this sphere, and you just project these lines of the graticules directly onto the plane. So you'll get different types of azimuthal projection systems. Okay, yeah. So then we have the genomic projection and similarly the stereographic projection. So here we are making use of these angles from the center of the sphere, and we are directly projecting on the plane. So these are mostly suited for the polar regions. Okay, so genomic and stereographic projections, they are suited for the polar regions because it is only covering up to a few degrees of latitude, both north and south pole. Yeah, sorry. So this is you can see mostly the upper latitude covering the poles, right? So this is where this is used, right? So now if you see the projection system, we have the cylindrical, conical, and the azimuthal projection. Then within this cylindrical and conical, we have the, as I've told you, like how many points this planes are intersecting with the sphere. And similarly, in which orientation they are, whether they are parallel to the axis or whether they're slightly angular to the axis of rotation, or they are oblique with the equator. So all these things are given by the aspect. Now, why so many projection systems? Okay, so why different types of projection systems? Again within that subdivision, why again so much? This is basically to see that like in a particular area. So whatever projection or the that we are using, it is it is working in the real world sense also. That means whatever you capture using this surveying techniques or the field based surveying, or the using your theodolite based surveying techniques, or the GPS or the DGPS. So they should match with the real world measurements that you're taking. So the main idea is that one. Okay, so in this context, you'll see like they always, map projections always introduce error and distortion. As I told you, like so in terms of the shape, so shape of the landmass. So here shape means the shape of the landmass. So from this like where the land and water is meeting, so that shape, the shape of different continents, the shape of the countries, right? So whether the true shape as they exist on the real sphere. Okay, so you see like the Asia has a particular shape, the European continent has a particular shape, the Australia has a particular shape. So this shape is only visual to us only if you look at probably at a very small scale. That means if you see it from a very huge distance only, those shapes are visible. Okay, so how do you basically represent that shape on the maps? Similarly, when you are doing these map projections, there will be a lot of distortions in terms of the areas. Okay, so the area as exists on the three-dimensional surface is different to when it comes to a two-dimensional surface. But whether the distortion is very huge and it is totally disrupting I mean, identify this as a particular country or a region. So that is what we need to bear in mind. And so similarly, the distance. Okay, so distance between any 2 points on a sphere will be different when it comes to a map, or when you flatten that three-dimensional surface, there is a change in the distance. And also the bearing, we call this direction as also the bearing. So whether the true north is, or it has shifted in a slightly different direction, right? So again, the shape and direction are useful for navigation. As I've told you, like intercontinental flights, pilots basically need to also have an understanding of where they are heading to. Okay, so in terms of a map, if it can provide you like where they are heading, so those who are in the control, traffic control, and also who are piloting the so it will be useful even for people who are going through navigation. They're going by seas, through boats, so it will be helpful for them, especially if they have a system like what do you call this a GIS based system for showing that navigation of the route, so they can easily visualize. Okay, and distances, especially like if you're doing a real world project, and if you want to measure the best distance, or you want to find out two features on the map, or two features on the sphere to that of a map, so whether it is really matching, or the shapes are whether intact, or the area. So like these are some of the properties that we need to bear in mind. So with respect to this only, there are plenty of projection system that have been discussed in the literature. There are separate books that will help you to understand all these things. So I'll not go further in detail, especially to tell you like what are the different types of projection system and what are the properties. Okay, so conformal means again it is conforming to the geometry, the shape of that one. Okay, so equivalent means the area, so it is preserving the area. Okay, bearing means the direction, right? So you can see what are the different types of projections here, what are the properties they preserve, and where they are used. Okay, so this slide basically you can go through, right? So this polyconic, as I've told you, is based on the multiple cones. So this can be used in a way like if you have a polyconic projection system, that you can prepare a global map, just like you have a global map of the entire Earth. So similarly, you can prepare the entire map based on this polyconic. Okay, so if you're using a single conic section, probably it will only serve the only a particular specific region or a specific hemisphere. But polyconic can be used to basically represent the entire globe. Okay, but again, you need to always have these compromise of the map properties. So you'll have distortions in one or the other form, as I've told before. Okay, right. But the universal transfer mercator is one such system which basically caters to each and to most regions of the surface of the globe. Okay, so this is a system that is based on the cylindrical projection. In fact, it's a polycylindrical projection system. So instead of using the entire regions of this the what you call the geographical coordinate, so only between 84° north to 80° south was used to in this particular system. And the entire zone is divided into 60 zones. I mean, the entire region between 84° and north to 80° south is divided into 60 zones, with each zone represented by 6 degrees longitude width. Okay, right. So this provides a very what you call a reasonable estimate for representing any portion of the the globe under this UTM, right? And we can use it for the any region of this globe, whether it is I mean Asia or America or the any other region. Okay, so with any you also have what is known as the false easting and false northing, because you are representing now this in a coordinate two-dimensional coordinate system, right? So two-dimensional coordinate system, we need to also mention like what is its the location of the origin with respect to the what you call the true origin of the Earth. Okay, so that is where it is called as a false easting and false northing. So the origin also shifts with respect to the datum. So on the projection, the same will be given to the projection system also, right? So when you're doing this projection system, you also need to bear at what scale you are mapping. So that is another factor that will also affect what type of projection you're using and how it will affect the accuracy of your map. Okay. So typically like 1 million maps are called as small scale maps, right? Basically you can go with whatever the global projection system that we have used. But so any scale of 1:1000, so you need to be a little wise in selecting the projection system because it can affect the accuracy of your linear to the angular units very drastically. Okay, so it also dependent on the scale. So what do you mean by scale is basically the comparison of the real world objects with respect to the map. Okay, so because we cannot map at 1:1 scale, definitely we use the different ways of representing the scale factor. Okay, so small scale means like you have a very big coverage. Large scale means you have a very regional coverage. You're only looking at a city or let us say a particular region of a particular area, right? Yeah, so with that background, now we have seen different how to capture the data in different data models, how to basically give the coordinate reference system or the map projection. So then how we can represent these features. So we have seen like this can be represented as point lines and polygons. Okay. And we can represent as satellite imagery, right? So satellite imagery is an example of the pixel based data, okay, which we also call it as raster data. We'll see, right? So this is the vector models where we are representing our geographical features based on whether it is having a what you call only a coordinate or only length. Like if there's only a point coordinate, we only give it as a point. If there is only a length or linear feature, we give it as a line. There is an area or let's say the circumference for a particular target, we call them as polygon. Okay. So like this, the different features can be represented as three major geometrical formats: point, line, and polygon. Okay. Similarly, with the help of these vector data, we can also model the geometric network model. Okay, so that means we can have a starting point, we have an ending point, or for a given starting point, what are the various ways basically that process can be followed. So all these things in the form of a network model, like electricity, like for instance, water supply, basically has a source and some endpoints. Okay, so the endpoints is basically the consumer points. So how we can represent that source and consumer points for water, electricity, or similarly the roads or the river flow, the catchment, the different linear channels of the catchment, the different orders. So all these things can be represented in a geometric vector model. So as I've told you, like we need to create all these vector models by starting from the point. So the good thing is, like in QGIS, everything will be asked upfront whether you want to create a point, line, or polygon data. So you need to first select those type of geometric data and then start creating your GIS layers, right? So in vector data, we also have what is known as a topological based formats. So as I've told you, like the spatial relationship are very critical for understanding some of the associations that we see in the real world. So that same have to be, if you have to incorporate those relationship in a vector model, then we need to go for a topological based model. So there are non-topological based model also, like your shapefile is an example of a non-topological model. But if you go to this geo database, it is an example of a topological based model. Okay. Right. So previously we had the geo-relational model. It was just basically mapping of the different rows of that particular layer with respect to the different attributes. Okay. So if we have this as one primary key or a common key among the different attribute titles, it can be matched. But we have seen like this geo-relational model does not work in the real world. Why? Because the real world, the situations are very different. We need to also incorporate what are known as the rules and behaviors. Okay. So just like how we follow the traffic rules, the same rules have to be imposed on the vector layers. Only then we can have the connectivity or the association or the spatial relationship among the different spatial layers. What I mean to say is, like, suppose if you are working parallelly on the points, lines, and polygons. So the points should know whether it is on the line or it's just by the side of the line. Okay. So on the line means, that means, let us say the line is an example of a road. So the point is directly clashing with the road, right? So that is not possible in the real world. A road, there should be basically, it's a free flow of the path. So you need to, so the topological rules and behaviors, they ensure that such, what you call indiscrepancies are not there. Okay. Or the road edges should match with that of the, what you call it, should end where the pedestrian, path or the corridor starts. So similarly, such rules can be enforced directly on a georelational, in a spatial database format that is not available in a georelational model. Okay. So raster is a pixel data format where the pixel value is directly the attribute. So that means the attribute values are inherent in the raster data. So we can represent the same points, lines, and polygons in the raster format only. But again, as you see, like the shape and the delimitation, that means the boundary of these features, when you represent it in a raster, they does not hold true. Okay, so there will be some, what you call randomness, or there will be very, what you call, there will not be very smooth, like how you get in a vector data. Okay. So these are some of the examples, like raster can be converted as into a thematic raster also, if you convert that into a group of categories. So we have seen in the thematic example, we can convert that as a group of values also. And you can also use this raster data to, calculate, you can derive it. You can derive NDVIs, you can derive NDWI, you can derive, you can combine multiple raster layers and derive information. So all these things possible in a raster data, right? Yeah. So this is what you can derive as a thematic raster from the original satellite data. Okay. So, but there are other forms of, where you can use the discrete data. That means if you have a point data, you can convert into a continuous data using these interpolation techniques. Okay. So that there are, various interpolation techniques. Some are linear, some are non-linear. Okay. So if you basically use the inverse distance weighted, it will give a very quick output, but again, the values will differ basically. So if you validate, you'll see that the values are not, in some areas, it is not matching. Okay. So some use nonlinear fitting techniques so that they match the shape of the, transformation. Okay. So if you plot a two-dimensional nonlinear curve on a two-dimensional graph, so the interpolation will try to match that nonlinear curve so that you'll get, exact representation of the values in this techniques. Okay. So what this technique does it will help you to derive the continuous information from a discrete data. So rainfall information mostly is captured as a discrete, although, sorry, you have, sensors that can capture the, measure the rain, quantum of rainfall, but mostly it is done using this weather station data only. So these weather station data are located at a discrete location. So use those locations and then you try to derive the continuous rainfall maps across the region. Okay. Right. So this probably I'll skip. So again, the other way of representation is the three-dimensional, data. From the vector data, you can represent it as a triangulated irregular network. So this is a vector way of representing a three-dimension. Okay. So if you want to generate, let us say, a topographical surveys in a three-dimensional vector data, that means using a geometry. So this is called as a TIN data. So this is formed by, a regular, what you call a combination of, irregular triangles. Okay. So which has a face, which is basically a polygon, line, and also the points. So these points are basically the known, what you call measured points. These are measured points. And from this, we are trying to create a surface that is, three-dimensional in nature. Okay, so this is also in vector format. So from this, a contour, elevation data, you can create contours, or from the contour data, you can revert back to elevation. So these are all basically used to represent the terrain. So just like your digital elevation models, digital, terrain models. So these contours and tints are basically a vector way of representing the same elevation interface. So these are also what you call iso surface also. That means they're representing the same elevation in particular, that particular region. So here the wider the triangles, that means the more plain that area is, the denser the triangles and very zigzag, the more undulating that particular region. Okay. Yeah, you can combine all these represent different forms of representations. Yeah, sorry. So sorry for the repetition of the slides because I had to basically collect all these slides from different presentations. Yeah. Yeah. Then it comes to the spatial data because we need to collect huge information and then maintain in the form of small folders, because file system anyway will not work because it is very difficult to remember all these things. So if you put it in a folder or especially in a spatial database, managing your spatial data will be easier. Okay. So some of the spatial database are proprietary, like how if you use a geodatabase in an ArcGIS, it is a proprietary, but it has good features. It has good features and controls that you can basically control how your project is shaping when you add more data or do the analysis. But there are open source also, like if you see in this QGIS, it is called as geo package. Okay, so that is also a similar in a form of a spatial database or a geo database that will help you to basically organize your spatial data in a file format, so that you can easily manage the data, add new data, impose the same rules like use as a geographical reference system when you are adding the data. So you should follow certain rules. You should follow certain checks and balances. So all these things can be done using a spatial database. And in QGIS, you can also do what is known as a simple graphical modeling. So modeling is basically like picking all these inputs and putting in a what you call a workflow, so that each and every inputs, whatever you provide, the outputs are extracted, and then the outputs are immediately provided to the next stage of processing. Okay, so it's a continuous workflow that is from the start to finish based on your what are the outcomes that you want, what are the features that you want to extract in terms of geometry or the pixel values or the attributes. So all this can be modeled. Instead of doing it step by step, we put it in a model. So that model could be a graphical model, or it could be already a developed model that is being used. So that also you can use in a QGIS platform. Okay. Yeah, so some of the other basics are there, like how GIS is basically, the GIS started with the real world observations, real world problems that we see day in and day out. So that is how it started. Okay, that basically a workflow that will help you to do the things in a systematic manner. So all these things are there, which I'll not go into because we are already overshooted the time. Yeah, so this is GIS environment, or the GIS tool is where you can combine different layers. Okay, so you'll get layers from the satellite imagery, from the other sources. So some you create on your own, some you borrow it, some you download it. So all these things, like for a particular region, let us say I'm working for a city of Hyderabad. So I can download the satellite imagery of Hyderabad. I can download, let us say, the road network of Hyderabad. I can download the urban, layer, GIS layer of Hyderabad. So some of these, these download options are there directly inbuilt in the plugins. Okay. So some of things probably will be shown that you can use it as a service, download the data, already created data, and then visualize how it is done. And if you want to model or you'd want to do the feature extraction, so all these things can be done in a GIS environment, right? Yeah, so probably how GIS is different. Yeah, so mainly the comparisons come with the CAD. So CAD also you can do a lot of, what you call, you can use the spatial data, because now the latest versions also come with the option of using this geographic layers also. Okay. So CAD is basically is meant for the civil engineers, but you can see like there is a lot of similarity between civil engineering and also the real world. Okay, because everything is has to be with us within some rules of the game. Okay, so that means how it ends, how it bisects, or how the what is the angle should be in the corners. So see that there's some set rules that we need to follow in the engineering domain. So the same rules can be incorporated in GIS also. Okay, so in that way, it's like they are now compatible in some of the data versions. Okay. All right. So what are the different components? Probably, as I've told you, like GIS only gives you different, scenarios. It will not directly provide you a solution. It will only give you scenarios by combining the proper data the process, the analysis, and also the models, you can arrive at different scenarios or outcomes, and it makes decision easier. So that is what it facilitates. It doesn't really provide you a solution directly, right? So it will only give you certain A, B, C type of scenario where you can select the best. And then implement it. It need not be the best on paper, but it may not be the best on field. So if you implement it, then you see the that results, then you can definitely, think of, creating what you call a proper solution or a dedicated solution out of that one. Okay, so these are some of the functions. I think there's a chain, probably you can see right from the data collection to the data publishing, data dissemination. So all these things, probably I'll not go, I'll share the presentation, probably you can, yeah. So again, what are different GIS data sources, the multiple ways in which you can collect, again, data conversions, okay. Yeah, so what we can do in a GIS, like it's an interactive, just like, now the, what do you call, these AI chatbots have become now very popular now. So just like how you interact with the chatbot or a AI chatbot, similarly the GIS will also provide you the same solutions. Okay, but only thing is you need to talk in the similar language, similar GIS language. So there is a query option, there is a way to extract the features, there is a way to visualize the features. So all these things can be done. Not only that, there is a standard toolbox that is available in QGIS that has the very advanced tools. In fact, now the latest machine learning tools, SAR tools, and hyperspectral tools are also incorporated directly into the latest version of the QGIS, that you can use it. The only thing, like our sir was also telling, is like you need to adapt to this QGIS environment, because the tools are mostly like parameters. I mean, you need to mention each and every parameter to, let us say, if you're running a what you call a supervised classification. I mean, this is there with the other softwares also, but I'm just trying to give an example. So it is mostly parameter driven. You need to feed each and every parameter to get the requisite outcomes. Okay. You can do a lot of modeling. As I told you, you can do a simple workflow modeling, or you can do a what you call a predictive modeling. You can also find out what will be the outcomes, how the scenario looks like. So all these things probably I'm telling orally the same you can try to visualize. Okay, so as I told you, for spatial data analysis, there is a dedicated repository in QGIS that I think you will get to understand in the coming classes. There are all the geoprocessing tools. Okay, so for raster, vector, what is the type of output that you want to create or you want to extract that feature, you can find it in the QGIS software. Okay. Yeah, so the workflows is what you need to understand, like given a set of data, how to basically extract the, let us say, the land use, land cover, different, let us say, the elevation models, topographic maps. So all these things, you have a vertical workflow. And then you can also do a lot of weighted analysis, like this what if analysis. Okay, so you can give different weights to different like suitability analysis or the yeah, the suitability analysis, if you want to, let us say, you want to establish a new, let us say, road or rail network. So, I mean, how suitable it is, whether it is really feasible. So first we need to, you can do it digitally, and then probably for collecting the real field data, you can assess whether it is really suitable or not. So what I'm trying to, just drive home is all these analysis or the what if analysis can be done in a GIS environment before you actually take it to the real world. Okay, so already it is being done. Probably at a professional level, come to understand in this particular, once you have a project of that sort, but you'll get to understand the basics, the elements, the components that are needed for building a professional GIS project. Okay. Yeah, there's plenty of visualization tools, open source and similarly in QGIS, right? So there's wide variety of GIS data that is available across various platforms. The web map services, I think as I've told you, like a lot of web map services are already been incorporated in QGIS. I think for the latest version, some of them are already by default. The others you need to install the plugins, but for the most, web-based visualization tools are by default. So you only install the latest version, you will have all these web services available. Okay. So using this open source tools, we can also build decision support system. Like means, so everything is what you call probably partially automated. That means the data flow will be done into this GIS decision support system. It will do the processing based on the workflow or the models that have been designed. Okay, and it will generate the different scenarios for the user who is actually looking after this decision support system to just say yes, no, go or no go. Okay, so that is a kind of what you call the scenarios the GIS decision-based support system can give to you. But again, you need to develop the proper infrastructure, proper front end, proper back end processing. So all these things have to be designed in order to generate a decision support or to create a decision support system. Okay. There are nodal agencies like who are doing the satellite acquisition, data, satellite reception, satellite dissemination from various platforms. So all these are available. So I think there are plenty of resources available on the internet that you can go through. Just a keyword I think should fetch you a good amount of information from the internet on this GIS that will help you to enhance your understanding and also clarify some of the doubts you may have. So I conclude here. So thank you very much for your kind hearing. So I'll take a few question and answers, and probably we can conclude the session there. Yeah,
Yes,
over
good
to you,
evening,
sir. Yes, ma'am.
Hello. Good evening, sir. Actually, I wanted to know about mobile GIS, sir, related. How we can integrate the mobile GIS with QGIS?
Yeah, actually, mobile GIS at the moment is used for the visualization and data collection. As far as I am aware, because you see, like the mobile has some limitations, especially in terms of what screen you can visualize. So you cannot do all the desktop GIS operations that you normally do on a mobile GIS. So mobile GIS, it's mainly used for collecting the field information. Okay, so that means you go with the mobile phone near the field and you want to collect the field information. Like suppose you are collecting the information related to a particular soil type or crop type. So do you go there, you take the picture using a mobile phone, you fill the relevant attributes that are given as the entry options, you fill them and you submit that one. So it basically helps in collecting the field information very quickly, which is again not an easy task. Okay, so at the moment that is how it is used, the mobile GIS. But if you slightly have the advantages having a big screen and you can run your desktop GIS and all those things, yes, mobile GIS. In fact, QGIS also has a mobile option also where that you can use. So that is how it is implemented at the moment. So probably in the in the coming days we can see like a full-fledged option as far as the using GIS in mobile phones is concerned. So is that clear, madam? I hope I clarified your doubt.
Yes, sir. Actually, if we want to implement some of the application and if we want to give to the Play Store, how we can have that app permission?
Yeah, so that means you are asking about the development of these apps.
Yes, sir.
Yeah, probably I think we have developed some under this Bhuvan field data collection platform. We have developed some mobile GIS. So our basically Bhuvan team has developed some of these apps. Again, they have developed it with respect to some specific project requirements of what to collect, right? Especially for this AP housing board, they have developed an app which collects the housing board. Some scheme is there which basically funds the construction of the houses for the citizens. Okay, so that means it is. So for that, they have developed a mobile app. Probably the technicalities of that one, because if you are developing a platform, what you call operating system based this application, so you need to follow whatever technicalities that is needed, madam. So that is the information I have. Probably you can connect back to me if you want to have more information on the mobile GIS.
Yes, sir. Thank you, sir.
Yeah, welcome, madam. So back to you, sir.
I have one clarification, sir.
Sir.
Sir, first of all, I would like to congratulate NRC scientists for a great sessions, 2 sessions. So my query is related to geodesy. So,
Yes, sir.
You presented on equation like arithmetic height is equal to ellipsoidal height minus geoid height.
Yes, sir.
Sir, actually, based on our GPS survey, we are getting the ellipsoidal height. So how
Yes,
can I do correction to the arithmetic height? Because the geoid separation model, along with my instrument, they have given on geoid separation model. But whether it is uniformly we can apply for our entire country, or else specifically we have to do the geoid separation model for each particular area. So this is the query from my side, sir.
Yeah, actually, again, the surveying is limited to the region in which you're surveying, sir. So it will hold good, like whatever the correction you are talking about. So that ellipsoid correction will hold good the region of that particular surveying. So if you want to, extrapolate it to beyond, you can extrapolate because anyway you have the points. And also we have a, what you call this, this control point network is there across the country. I mean, some of it is restricted, but you have this, surveyed points where each and every location is measured accurately using GPS and using that ellipsoidal, whatever you have taken. So if you are using a survey on your own and you're surveying a limited points, it will hold true to that particular location research. So you'll get exact matching and you can use the same equation to arrive at the, what you call the, whatever the true height is there. But beyond that, if you go, either you have to use the standard GCP library of the network of that library to have that height estimation. Otherwise, it will be you will have some variations or the deviations in the value.
Sir, in my survey, actually, I have collected the GCP information, that is the reduced level from the Survey of India, and the base station, that is my control station. I have applied that correction, that height correction. when I'm establishing the secondary points, like this was some road project. So when we were do the design, with respect to the control points, we have established the n number of secondary reference points, and based on that we have completed the entire survey, topography survey. So while we were doing the design, actually the cutting and filling, that volume and the actual say the map output and the actual volume are not matching. So is it due to the this geoid separation or anything else?
No, sir. Because you said like you have used the compared it with the Survey of India, because Survey of India uses 3 different types of projections, sir. Now for the latest, they are using the LCC, Lambert confirm. No, UTM also they are using, but for especially for the large scale maps, they are using the Lambert confirm. So there will be a variation, sir. But here the probably from an application standpoint is how far this deviation is, whether it is in acceptable limits or beyond that limit is what you have to take a call.
Okay. See, whenever we are collecting the data from the field, even if I am superimposing the satellite data, what I am collecting from the either NRC, so that is not actually matching even XY. So that in that case, what kind of correction I have to apply either in the map or in my data?
Maps, because see, maps are already they already have a projection, so that means only thing they are digitized and they are used. The best thing is to do, you have to reproject your data or whatever the GIS layers you have. So it's better to that way rather than reprojecting the map.
Thank you, sir. Thank you.
Yes, sir.
Yeah.
Yes, sir. So
Any other query? There are few queries in the chat box. Can we go through them or?
yeah, I'll take a few of them, sir.
Yeah.
Mobile, I think we have already discussed how to decide the type of projection to be used. I think you can minimize that effort, sir, by downloading the what you call the georeference data products. Okay, so most of the GIS players that that are freely available, they come with a predefined projection system. Only thing is you have to see whether that projection system is what is your required projection system. So if there is a different projection system that you are using, probably you need to reproject those projection system. But otherwise, you can minimize that understanding by downloading the already georeferenced data sets. Okay, so if you are downloading the data of our country, mostly they come with the what you call the geographic reference system. So they will have a datum, what is the projection type, what is the pixel size. So all this information is already defined there, so that you don't have to again go through the process of reprojecting or recorrecting the projection, right? Yeah, so DEM is basically a raster representation of the elevation information. So the whatever the average elevation value is there for a particular pixel. Like for example, if you take the 30-meter DEM, aster DEM, so that means the average elevation, that means a point, if you would point the average elevation value, let us assume that the center of the pixel is the average elevation value. So that is the value that is denoted for the entire pixel. Okay, so that is how the elevation value of that particular raster type will tell you. Okay, so like morning also we were telling, like if you want to have a better estimate of the terrain, you either go for a lidar survey or you go for this photogrammetric measurement. Then you'll get an exact representation of the elevation.
Yeah, hope all the queries are answered. Is there any other query? I would like to inform the participants that we will be sharing the PDF presentation. Both the presentations we will be sharing in the e-learning portal, as well as the recording of the both the sessions. We will upload them. If you still have any queries regarding the basics of remote sensing and GIS, you can post it in the course forum. I will take them to the concerned faculty, or you can even post in the WhatsApp group. For now, many participants are still enrolling in the e-learning platform, and there is an issue with confirmation mail. We are trying to look into it. Already we have about 695 participants enrolled in the e-learning portal. We will meet tomorrow again at 10 o'clock. The session will be uploaded on the e-learning portal on introduction to QGIS and installation of QGIS, followed by another session on open access datasets. In the afternoon. We will be covering many of the sources of datasets, both vector and raster datasets. I hope then it will answer many of your queries related to where you can find the data. So on behalf of National, the session and PPT will be uploaded in the e-learning platform. E-learning nwa@pune.gov.in. You have to enroll for the course. To all the registered participants, we have sent the detailed step-by-step procedure to enroll, register and enroll for the course. In the course page, you will find all the information. Yeah, we will be uploading a quiz at 6 o'clock today. Which we will keep, it will be a simple MCQ question type quiz, and we will keep it open for 24 hours. You can attempt it. So I thank, on behalf of National Water Academy, I thank Shri Harish for delivering two very informative and elaborate sessions covering the basics of remote sensing and GIS. Thank you, sir. Thank you very much for accepting our invitation and delivering these sessions.
Thank you, sir.
Yeah, please, you can share the presentations, then we will share them to the participants.
Sure, sir. Thank you all, the audience, for your patient listening. Thank you, sir, for this opportunity, and I wish you all the participants the very best and a very fruitful learning for the training program. So thank you.
Thank you very much.